before the forests breathed, before the seas bore fish, before even the smallest cell stirred in the deep, there was only dust. Dust of ancient stars, dust that drifted through the newborn heavens until the fires of creation were kindled once more. This is the first saga of our world, the Age of Fire, the Hadean. To understand the birth of the Earth, we must begin long before the world existed. Roughly 4.6 billion years ago, a vast cloud of gas and dust, known as a molecular nebula, began collapsing under its own gravity. These clouds can span tens to hundreds of light years across, containing enough material to form thousands of stars. At the center of this collapsing cloud, matter accumulated into a growing sphere that would ignite into the star we now call the Sun. But not all of the material fell into the young star. Much of it flattened into a spinning disk called a protoplanetary disk. This hot, shining disk extended for billions of kilometers, and within it, dust particles began colliding. At first, these collisions formed grains only micrometers across. But gravity is patient. Grain by grain, pebble by pebble. These particles grew into objects kilometers wide known as planetesimals. Some of these bodies would eventually become the planets. Others would remain behind as asteroids and comets. Within about 10 million years, one growing protoplanet in the inner solar system had accumulated enough mass to begin shaping the world we now stand upon, the young Earth. Early Earth looked nothing like the beautiful blue world we know today. Instead, its surface was dominated by a global magma ocean, a sea of molten rock hundreds of kilometers deep. Temperatures across the surface likely exceeded 2,000 degrees Celsius. At these temperatures greater than what we see in blast furnaces, rock flows like water. The planet glowed red in space, radiating heat into the darkness. The reason for this intense heat came from three main sources: constant asteroid impacts, gravitational compression, and radioactive decay of early isotopes. During this time, the solar system was still crowded with debris. Massive impacts occurred frequently, each releasing energy equivalent to millions of nuclear weapons. These impacts repeatedly melted Earth's crust. And yet, deep within the planet, something important was happening. Heavy metals, particularly iron and nickel, began sinking toward the planet's center in a process called planetary differentiation. Within perhaps 30 to 100 million years, Earth separated into layers: a dense iron-nickel core, a thick rocky mantle, and a primitive crust. This internal structure would become crucial to Earth's long-term stability. Without it, our planet might never have become habitable. Yet the most violent moment in Earth's early history was still to come. Sometime around 4.5 billion years ago, a protoplanet roughly the size of Mars collided with the young Earth. Scientists refer to this lost world as Theia. This collision occurred at speeds of roughly 10 kilometers per second, that is 36,000 kilometers per hour. The energy released was so enormous that much of Earth's outer layers were vaporized. Entire oceans of molten rock were blasted into orbit. The planet may have briefly become a glowing sphere of magma and vapor. But from that destruction came something extraordinary. The debris ejected into space formed a disk around Earth. Over the next thousands of years, gravity pulled this material together, and from it formed the moon. Today, the moon sits roughly 384,000 kilometers away, slowly drifting outward at 3.8 centimeters per year. But early in Earth's history, it was far closer. The moon may have appeared 10 times larger in the sky than it does today, and its gravity stirred enormous tides in the Earth's molten surface. This event helped stabilize Earth's rotation and tilt, factors that would later influence climate and habitability. Without the moon, life on Earth might have evolved very differently. For hundreds of millions of years after the moon formed, the inner solar system remained a dangerous place. Asteroids and comets continued crashing into the young planets in an era known as the Late Heavy Bombardment. This bombardment peaked 4.1 to 3.8 billion years ago. Evidence for it comes largely from the moon, whose cratered surface preserves the scars of that violent time. Some of these impacts were enormous. Objects hundreds of kilometers wide slammed into Earth. Each impact could sterilize large portions of the planet's surface. And yet, these same impacts may have also delivered something vital: water. Many scientists believe Earth's early oceans were partly delivered by water-rich asteroids and comets. As the rate of impact slowed, Earth began cooling. Volcanoes continued to release gases into the atmosphere, forming a thick blanket of carbon dioxide, nitrogen, methane, and water vapor around the surface of the Earth. But as the planet cooled below 100 degrees Celsius, something remarkable happened. The water vapor condensed. Rain began falling. Not for days, not for years, but for millions of years. Gradually, this rain collected into the first global oceans. By about 4.3 billion years ago, liquid water may have already existed on Earth's surface. This discovery came from ancient zircon crystals found in Jack Hills in Western Australia, which suggests surprisingly early oceans. These waters would become the cradle of life. And as the fires faded, the heavens grew quieter, and beneath dark and restless skies, the first oceans gathered upon the wounded world. But within those waters, something waited, something small, something patient. For soon, in the depths of those ancient seas, life would rise, and the next saga would begin. The Archean.